On this rock platform at Maroubra Beach, you might not think there's much going on. Just a few snails clinging to the surface, right? But look closer, and you'll find a hidden story of adaptation unfolding in miniature. I'm investigating how tiny differences in habitats, like being submerged in a rock pool versus exposed to the sun, or being across intertidal zones, could shape the shell morphology of Nerita melanotragus, also known as the black nerite, which is a common intertidal gastropod. Even this species here on this platform could show that evolution in its smallest form might not stand still. Although Nerita melanotragus is widespread across southeastern Australia and New Zealand, there's surprisingly little research on how its shell morphology varies within a single site across microhabitats. Most studies focus on interspecific variation, or large-scale environmental gradients. These are the following studies that specifically look at Nerita melanotragus. Regardless, we don't know yet how fine-scale habitat differences, like tidal zones or rock pool presence, affects morphology within this species. This matters because there is a limited understanding of how environmental factors shapes the trait expression of this species within dynamic ecosystems, like the intertidal zone. My study allows me to explore phenotypic plasticity, which is the capacity of organisms to adjust their morphology in response to environmental conditions. By exploring this, it enables me to identify patterns that may reflect non-random trait distribution across habitats. So knowing this, my research questions were: does shell morphology vary across tidal zones? Within each zone, do individuals in rock pools differ from those on emergent surfaces? And finally, which traits are most affected by microhabitats? I conducted my study at Maroubra Beach on a single rock platform to control for geographic variation. I sampled individuals of Nerita melanotragus across three tidal zones: high, medium, and low. Within each zone, I also compared two microhabitats: rock pools and emergent surfaces. All sampling was done a few hours before low tide to control for temporal exposure, and only this species was used to eliminate interspecific variation. For data collection, I laid out a 5-meter transect within each tidal zone, totaling in 15 meters. Every zero point 0.5 meters, I selected one individual closest to the transect mark. If there was a cluster, I used a random number generator to reduce selection bias. For each individual, I measured 4 morphological traits using calipers. This included shell length, shell width, aperture length, and aperture width, all in millimeters. By controlling for species, site, and sampling time, I isolated the effects of tidal zone and microhabitat. This design reflects the principle that variation in form is often a response to variation in function or environment. So if shell traits differ consistently across habitats, it may suggest environmentally driven morphological variation, possibly through phenotypic plasticity. Each element of my methodology is designed to address a specific research question. By comparing individuals across tidal zones, I examine whether environmental gradients are associated with variation in shell traits. Within each zone, by comparing individuals from rock pools and emergent surfaces, it allowed me to explore whether microhabitat conditions could drive morphological divergence. Measuring specific traits, including shell length, width, and aperture dimensions, helps identify which features are most responsive to habitat variation. Based on these environmental differences, I predict that individuals in rock pools may exhibit wider apertures, potentially reflecting greater aquatic exposure and reduce desiccation stress. I also predict shell size to increase in lower tidal zones, where prolonged submersion may ease physiological constraints. If these patterns emerge, they could indicate phenotypic plasticity, where morphology shifts in response to environmental cues, or non-random trait distribution shaped by habitat filtering. While this study doesn't directly test for adaptation, documenting these associations lays important groundwork for understanding how environmental variation can influence trait expression in intertidal gastropods. If shell morphology varies predictably with habitat type, it suggests that Nerita melanotragus may exhibit environmentally induced plasticity. This matters because plasticity can buffer populations against environmental change, allowing persistence with immediate genetic shifts. It also highlights the importance of conserving habitat diversity in intertidal zones, since even subtle differences can influence species traits and ecological roles. While I can't test for adaptation directly, documenting these patterns is a first step towards understanding how morphology responds to environmental pressures and how evolution might operate in dynamic coastal ecosystems. Thank you for watching, and next time you're at the beach, take a closer look. Evolution might be unfolding right under your feet.